A reducing agent is an element or compound that loses an electron to another chemical species in a redox chemical reaction. Since the reducing agent is losing electrons, it is said to have been oxidized. If any chemical is an electron donor, another must be an electron recipient. A reducing agent is oxidized because it loses electrons in the redox reaction. Thus reducers are oxidized by oxidizers and oxidizers are reduced by reducers. Reducers are by themselves reduced and oxidizers are by themselves oxidized. A reducing agent typically is in one of its lower possible oxidation states and is known as the electron donor. Examples of reducing agents include the earth metals, formic acid, and sulfite compounds. For example, consider the overall reaction for aerobic cellular respiration, C6H12O6, S, plus 6O2, G, A6CO2, G, plus 6 hours 2O, L. The oxygen is being reduced, so it is the oxidizing agent. The glucose is being oxidized, so it is the reducing agent. In organic chemistry, reduction more specifically refers to the addition of hydrogen to a molecule, though the aforementioned definition still applies. For example, benzene is reduced to cyclohexane in the presence of a platinum catalyst, C6H6 plus 3 hours to a C6H12. In organic chemistry, good reducing agents are reagents that deliver H2. Historically, reduction referred to the removal of oxygen from a compound, hence the name reduction. The modern sense of donating electrons is a generalization of this idea, acknowledging that other components can play a similar chemical role to oxygen. Characteristics: consider the following reaction: 2, Fe, Cn, 6, 4 plus Cl, 2 2, Fe, Cn, 6, 3 plus 2 Cl. The reducing agent in this reaction is Fe cyanide 6, 4. It donates an electron, becoming oxidized the ferricyanide 6, 3. Simultaneously, the oxidizer chlorine is reduced to chloride. Strong reducing agents easily lose electrons. An atom with a relatively large atomic radius tends to be a better reductant. In such species, the distance from the nucleus to the valence electrons is so long that these electrons are not strongly attracted. These elements tend to be strong reducing agents. Good reducing agents tend to consist of atoms with a low electronegativity, the ability of an atom or molecule to attract bonding electrons, and species with relatively small ionization energies serve as good reducing agents too. The measure of a material to oxidize or lose electrons is known as its oxidation potential. The table below shows a few reduction potentials that could easily be changed to oxidation potential by simply reversing the sign. Reducing agents can be ranked by increasing strength by ranking their oxidation potentials. The reducing agent is stronger when it has a more positive oxidation potential and weaker when it has a negative oxidation potential. The following table provides the reduction potentials of the indicated reducing agent at 25 °C. To tell which is the strongest reducing agent, one can change the sign of its respective reduction potential to make it oxidation potential. The bigger the number, the stronger the reducing agent. For example, among Na, Cr, Cu and Cl, Na is the strongest reducing agent and Cl is the weakest one. Common reducing agents include metals potassium, calcium, barium, sodium and magnesium, and also compounds that contain the Ha ion, those being NaH, LiH, LiAlH4 and CaH2. Some elements and compounds can be both reducing or oxidizing agents. Hydrogen gas is a reducing agent when it reacts with nonmetals and an oxidizing agent when it reacts with metals. 2Li, S, plus H2, G, A2LiH, S. Hydrogen acts as an oxidizing agent because it accepts an electron donation from lithium, which causes Li to be oxidized. Half reactions: 2Li, S, 0 are 2Li, S, plus 2AH20, G, plus 2A are 2Ha, G, H2, G, plus F2, G, A2HF, G. Hydrogen acts as a reducing agent because it donates its electrons to fluorine, which allows fluorine to be reduced. Half reactions: H20, G, A2 hours plus, G, plus 2AF20, G, plus 2A24, G. Importance: reducing agents and oxidizing agents are the ones responsible for corrosion, which is the A-E degradation of metals as a result of electrochemical activity. Corrosion requires an anode and cathode to take place. The anode is an element that loses electrons, thus oxidation always occurs in the anode, and the cathode is an element that gains electrons, thus reduction always occurs in the cathode. Corrosion occurs whenever there is a unregistered trademark SA difference in oxidation potential. When this is present, the anode metal begins deteriorating, given there is an electrical connection and the presence of an electrolyte. Example of redox reaction: the formation of iron, 3, oxide. 4 Fe plus 3O2 or 2 Fe 23 plus O36, in the above equation, the iron has an oxidation number of 0 before and 3 plus after the reaction. For oxygen, the oxidation number began as 0 and decreased to 2A. These changes can be viewed as two half reactions that occur concurrently: oxidation half reaction, Fe0 or Fe3 plus 3A, reduction half reaction, O2 plus 4A or 2O2A. Iron has been oxidized because the oxidation number increased. Iron is the reducing agent because it gave electrons to the oxygen. Oxygen has been reduced because the oxidation number has decreased and is the oxidizing agent because it took electrons from iron. Ferric, common reducing agents: lithium aluminum hydride, nascent hydrogen, sodium amalgam, diboron, sodium borohydride, compounds containing the SN2 plus ion, such as tin, 2, chloride, sulfate compounds, hydrazine, zinc mercury amalgam, diisobutyl aluminum hydride, Lindlar catalyst, oxalic acid, formic acid, ascorbic acid, phosphites, hyperphosphites, and phosphorus acid, dithiotritol used in biochemistry labs to avoid SS bonds, compounds containing the Fe2 plus ion, such as iron, 2, sulfate, carbon monoxide, CO, carbon, tris, 2-carboxyethyl, phosphine. HCl, several common reducing agents and their products. See also, organic reduction, oxidizing agent, electrochemistry, electrosynthesis, corrosion, electrolyte, redox. References. Further reading: Chemical Principles, The Quest for Insight, 3rd edition. Peter Atkins and Loretta Jones P. F. 76, external links, table summarizing strength of reducing agents at the Wayback Machine.